Welcome back. Here you see a thin stream of water running out of a burette. Notice how the water is attracted to an electrostatically charged balloon that my son rubbed through his hair. Now let's do the exact same demonstration, but this time replacing water with hexane. And nothing. The stream of hexane is not deflected. The reason this happens is because water is a polar molecule and hexane is nonpolar. In this lesson and the next, Polar and Nonpolar Molecules, Parts 1 and 2, we will learn how to predict whether or not a molecule is polar. Recall we've already learned how to determine if a bond is polar. So let's start with a review of that because molecular polarity is built upon bond polarity. Fill in the blanks in the paragraph you see here about bond polarity. Stop the video now. Silicon and chlorine are not the same element, so they have different electronegativities. Chlorine is closer to fluorine than silicon on the periodic table, and therefore we predict it has a higher electronegativity. And the element with the higher electronegativity always has the partial negative charge in a bond because the shared electrons, which are negative, are pulled closer to that side of the bond. So each of the 4 bonds in silicon tetrachloride would be a polar bond. A polar bond is one in which one end of the bond is partially negative and the other end is partially positive. On the other hand, a polar molecule is one in which one end of the entire molecule is partially negative and the other end is partially positive. So the focus of this lesson is to learn how to look at a structure and determine if the entire molecule is polar or nonpolar. I think the best way to do this is to go right to an example. Let's start with a simple diatomic molecule, hydrogen chloride. Use the following steps to determine if a molecule is polar or nonpolar. First, draw the Lewis structure. Here it is for HCl. If you aren't sure where that came from, you should immediately stop this lesson and go back and review how to draw Lewis structures. Next, sketch the shape of the molecule. In this case, it's really simple because there are only 2 atoms, so it must be linear, like this. Third, assign partial negatives and partial positives to each polar bond. In this case, there is only one bond, and the chlorine is given the partial negative since it's more electronegative than hydrogen. Next, determine where the centers of all the partial positives are and where the center of all the partial negatives are. Well, what do we mean by this? Let's start with the partial positives. Let's locate all of them. Well, there's only one, right here. It's that hydrogen. So the center of positive charge is right on that hydrogen. Now for the negative. Well, there's only one partial negative, right here. So the center of the partial negatives is right on that chlorine. All right, final step. If those 2 centers you just determined are in the same place, i.e. they coincide, then they cancel out and the molecule has no negative or positive end. And the molecule is nonpolar. If the centers of charge are in different places, however, then the molecule is polar. Well, in this case, the centers of charge are in different places. So this molecule has one end that is negative and one end that is positive, and the molecule is polar. Let's now try another simple diatomic, N2. First, we draw the Lewis structure. For the shape, since it's diatomic, it must be linear. 2 atoms can only be connected by a straight line. Now we need to add the partial negative and partial positives to all the bonds, but we quickly realize there's only one bond, and it's a nonpolar bond since both nitrogens have the same electronegativity. Therefore, there are no partial negatives and partial positives. So we can skip step 4, and step 5 tells us the molecule is nonpolar because there are no partial charges in the entire molecule. Therefore, N2 is a nonpolar molecule. It has no negative end or positive end. Now, after these first 2 examples, you may be thinking, this is easy. If the bond is polar like in HCl, then the molecule is polar. And if the bond is nonpolar like in N2, the molecule is nonpolar. Well, of course that is true, but only if the molecule is a simple diatomic. Most molecules have more than 2 atoms, however. So now let's pick up the degree of difficulty a bit. Consider carbon dioxide. First, here you have the Lewis structure. Well, since we have 2 regions of electron pairs around the central atom, here and here, we predict the electron pair geometry is linear. Step 3 is to determine bond polarity for all bonds. Unlike our first 2 examples, which only had 1 bond each, this time we have 2 bonds, here and here. For the bond on the left, the oxygen, being more electronegative, gets the partial negative, and the carbon gets the partial positive. Same thing for the bond on the right. We don't need to rewrite another partial positive on the carbon because it's directly on the carbon, just like the first one. Now step 4 is to determine the centers of charge. Well, the center of positive is easy. There's only one positive, so the center of positive must be directly on the carbon. But notice we have two partial negatives. So the question is, where is the center of those two negatives? Well, hopefully it's obvious the center of this oxygen and this oxygen is directly on the carbon. So the center of negative is also on the carbon. Since the centers of negative and positive coincide, that is, they are in the same place, we would say they cancel out and the molecule is nonpolar. It has no positive or negative end. Note that even though this molecule did have polar bonds, the molecule as a whole is nonpolar. Does that mean this is always the case? Well, let's consider water, one of the molecules we saw in the introductory demonstration. First, the Lewis structure. Here we notice there are 4 regions of electrons around the central atom. 1, 2, 3, and 4. Therefore, for step 2, we determine the electron group geometry is tetrahedral, and the shape looks like this. Now, unshared pairs, these two pairs, do play a role in the polarity of the molecule, but it's a minor impact compared to bond polarity. Therefore, once we've determined the actual shape, we can imagine the unshared pairs are not there. Just focus on the bonds. So for step 3, we add in the partial charges. In each of the two bonds, the hydrogen is less electronegative and therefore partially positive, and the oxygen is partially negative. For step 4, we realize the center of negative is directly on the oxygen, since that was the only partial negative. For the center of positive, we have one positive here and one positive here. So to find the center of those two positives, imagine a straight line between the two, and the center of that line is the center of positive charge. Finally, in step 5, we can see the center of negative here is not in the same place as the center of positive here. Therefore, water is a polar molecule. Unlike the previous example, carbon dioxide, here we had a molecule with polar bonds that was also a polar molecule. Now, silicon tetrachloride, the same molecule we saw in the review question to start off the lesson. First, we draw the Lewis structure. Next, to determine the shape, we see there are 4 regions of electron pairs around the central atom. 1, 2, 3, and 4. Therefore, for step 2, we again sketch a tetrahedral shape. Unlike water, which had unshared pairs on the central atom, notice all regions on the central atom here are bonds. For step 3, we assign partial charges to all 4 of those bonds, as shown here. Now, since this is our first true 3-dimensional molecule, I think it would be helpful if I showed you a model. Here's a model of silicon tetrachloride. As we've seen, each chlorine is partially negative, and the silicon is partially positive. Determining the center of positive is pretty clear. It's right here, since silicon is the only positive. But to determine the center of negative, it helps to have some good spatial visualization. If it's not obvious at first where the center of all 4 negatives is, then try this. First, focus on just 2 of them. Say, here and here. And ask yourself, where's the center of those 2? Well, if we drew a line between those 2 atoms, the center point of that line would be the center of negative charge for those 2 atoms. That is, right here. Now do the same thing for the other 2 partial negatives. The center of this negative and this one is right here. Now to get the center of negative for the entire molecule, ask yourself, where's the center of those 2 negative points here and here? Hopefully it's clear that the center of those 2 is right smack in the middle. So the overall center of negative is on the silicon, just where the center of positive is. Since the center of positive and negative charge coincide, silicon tetrachloride is a nonpolar molecule. By the way, Have I mentioned the models I've been using are the giant-sized ones? It says right here on the box. When I was single, I used to take these home with me on the weekend. Then I could tell people I was spending time with a supermodel.
Oh, a funny man. That's the matter with you.
Let's try another one. This molecule is called formaldehyde. First, you'd have to go through your Lewis structure steps, and hopefully you'd come up with this. For step 2, we count up the regions of electrons around the central atom. This has 1, 2, and 3. Therefore, the electron group geometry is trigonal planar. Our next step is to assign partial charges. So if we first consider the C to O bond, the oxygen gets the partial negative due to its much higher electronegativity than carbon. Now for the C to H bonds, the carbon this time gets the partial negative because it's slightly more electronegative than the hydrogen. If you're wondering, how can carbon be partially positive and partially negative at the same time? Well, of course it can't be. It's only one or the other. But what we're doing here is sort of a trick to determine the overall centers of negative and positive charge. Let's first consider the centers of negative. We have one negative here on the carbon and one here on the oxygen. So the center of those two negatives is between those two atoms where you now see the green negative sign. Moving on to the center of positive, we have a positive here, here, and here. So to find the center of those three, imagine a triangle connecting those 3 points. And the center of the triangle would be the center of the positive charge, as you see here with the red positive sign. Since the negative charge here and the positive charge here are not in the same place, formaldehyde is a polar molecule. Before we go further, let's pause a moment to ask some conceptual questions. Try the one you see here. True or false? A molecule containing polar bonds must be a polar molecule. Stop the video now. False. As we saw with silicon tetrachloride and carbon dioxide, they both had polar bonds, but the overall symmetry of the molecule caused the partial charges to cancel each other, and the molecules were nonpolar. Speaking of silicon tetrachloride, we've seen it's nonpolar. Would it still be nonpolar if we replaced one of the chlorines with a bromine, as shown on the screen? Stop the video now and consider your answer. All 4 of the peripheral atoms are still negative, but the partial negative of the bromine is less than the partial negative of the chlorine. Chlorine is more electronegative than bromine, thereby making the silicon to chlorine bond more polarized than the silicon to bromine bond. The result of this is that the center of negative is no longer on the silicon, but rather somewhere below the silicon, as shown by the negative sign. Since the center of positive is still directly on the silicon, this compound is a polar molecule. Okay, last structure, xenon tetrafluoride. First, you would be responsible for coming up with a Lewis structure that looks like this. Now I want you this time to determine the actual shape. Stop the video now and sketch the shape of the molecule. Here's the actual shape. We get this because there are 6 regions around the central atom. Here, 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 and here. 6 regions gives us the octahedral shape you see. But we need to remember that when an octahedral has 2 unshared pairs, here and here, they go on opposite sides, as shown. Well, this is critical in assessing the polarity of the molecule. We move on to step 3, and we place the appropriate partial charges, with fluorine, of course, always being partially negative, since that has the highest electronegativity. Now, to determine the center of positive and negative again, it's probably best that I show you a model. Here's a model of xenon tetrafluoride. We've got 4 fluorines, 1, 2, 3, 4. We've got the xenon in the center, and the unshared pairs here and here. Let's remove those unshared pairs since we just want to now focus on the bonds. Since each fluorine is partially negative, the center of those 4 fluorines, which make a square planar molecular geometry, would be right smack in the middle, on the xenon. And the center of positive is also on the xenon, since xenon was the only partial positive. So the centers of positive and negative are in the same place. When this is the case, the molecule is nonpolar. Okay, let's review. For diatomic molecules, like the ones you see here, it's really simple. If the bond is polar, the molecule is polar. And it's not even necessary to write out all that you see here. As soon as you know the formula has only 2 atoms, and those atoms are different, like in HCl here, the bond is polar and the molecule is polar. Of course, for other molecules, you have some more work to do. Ultimately, you need to sketch the shape and determine the center of negative and positive charge. If the centers are in the same place as in carbon dioxide, then they cancel and the molecule is nonpolar. If the centers are in different places, as in water, then the molecule is polar. Well, thanks for listening, and see you soon for polar and nonpolar molecules, part 2, which is a much shorter lesson. At the conclusion of that lesson, we'll come back to the balloon demo we saw at the start of this one, and we'll explain why the water was deflected by the balloon, but the hexane was not.